Okay, so Charles' law is going to relate volume and temperature. So in this case, we know that volume is directly proportional to the absolute temperature. So that means that if we increase the temperature, it's going to also increase the volume. If we decrease the volume, it will also decrease the temperature of the gas. All right, so this picture over here is actually a picture of a combustion engine. So a combustion engine works by filling up this chamber right here, this combustion chamber with gas, and it ignites the gas in order to heat it up, and then the gas expands. So when the gas gets hot, it expands, and it allows this piston here to turn, and that's what creates the power that's going to make your car move, or how the engine in your car works. So if we increase temperature, we increase volume. If we decrease volume, we decrease temperature. So the equation looks like this. It's a division relationship. You have V1 over T1 is going to be equivalent to V2 over T2. So let's do just a quick example. So it says we have a sample of carbon monoxide gas, and it occupies 3.2 liters at 125 degrees Celsius. At what temperature will the gas occupy a volume of 1.54 liters if the pressure remains constant? So remember, we have to keep one of the variables constant because we know all three of those are intertwined. So in this case, it's pressure. So we're just looking at volume and temperature. And so this is the equation that we're going to use. So let's start by defining our variables. We have the initial volume as 3.2 liters. And we have the initial temperature as 398 Kelvin. So keep in mind that, remember I said that we have to do our gas laws in Kelvin and not in degrees Celsius. So I've just taken 125 and added 273 to it. This is 398.15 because this is the PowerPoint from my AP Physics, and we use a little bit more exact of a number. Now, the final volume is 1.54 liters. So what is the final temperature? So let's, again, just think about it conceptually. We said that volumes, as they decrease, temperatures also decrease. So they're proportional to one another. So if we look, we went from 3.2 liters to 1.54. That's about a half. So we should expect that our temperature gets cut in half as well. So we would estimate that it would be somewhere around, roughly around 200 Kelvin. So let's go ahead now and just do the algebra. So I want to solve for T2. And so in order to do this, I would actually cross multiply. So I would multiply T2 times V1 and T1 times V2. And then I would divide by V1. So I've got V2 times T1 over V1. Now you can just plug in numbers too and then solve for the variable, or you can algebraically solve first, whichever is easiest for you. And then we just need to plug in the values that we have. So we've got 1.54 liters times 398 Kelvin divided by 3.2 liters. My liters will cancel, and I'll be left with Kelvin. So if I multiply 1.54 times 398 divided by 3.2, I get 192 Kelvin, which is what I estimated. So it's a good practice to sort of start to think about things conceptually first, so that at the end, when we get our answer, we can say, yes, this answer does make sense, or no, it doesn't, and maybe I did something wrong algebraically.